Thank you for joining us today. My name is Sabrina Devone, and I will be the moderator for today's webinar. I am a member of our Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. Everyone on the Innovation Builders team and the speakers on this call are remote working parents and grandparents, and we applaud their ability to find time to share their knowledge in addition to serving their clients while juggling the intersection of their career and home lives. Today's technical presentation is about carbon capture and how we could build a better world through it. The goal of today's presentation is to help you. We will talk about how carbon capture affects you directly as an owner-operator, using practical information on cost, benefits, and opportunities. To that end, our agenda is focused on answering the questions that you may have. Why consider carbon capture and what opportunities are available? Who has been acting on these opportunities? What options do you have for collection and disposal? How to integrate those options with the goals of an existing facility? And of course, an understanding of the capital cost breakdown based on real-world experience. We have Fluor experts with us today to help answer those questions. Our speaker today is John Isley. John has over 26 years of process engineering, design, and leadership experience at Fluor. He managed engineering teams in all phases of design across multiple offices and in construction environments. He has technical expertise in petroleum refining technologies, including distillation, hydroprocessing, hydrogen generation, gasification, and syngas technologies, including CO2 capture, utilities, and gas processing. Joining John is Matt Reisdorf. Matt has more than 22 years of experience in the process design of refineries, chemical complexes, and in the work processes and execution of process design work. He provides expert leadership in crude vacuum system design, hydroprocessing, and overall facility configuration. He has led teams in the design of refinery reconfigurations, natural oil chemical facilities, and ethylene-based chemical complexes. He has published technical publications related to vacuum distillation, hydroprocessing, and rapid process design techniques. He has led design efforts ranging from small studies to multi-billion-dollar, multi-unit designs. Fluor has a strong safety-driven culture. As such, it is customary for us to start our meetings with a safety topic. So I'll ask John to unmute his line to share a brief safety topic and begin.
Thank you, Sabrina. My name is John Isley, and as Sabrina said, I'm going to begin the discussion with you over the next hour by starting off with a safety topic. On this topic, I think it's important to orient ourselves to the hazards that are inherent of facilities handling concentrated CO2. The National Institute for Occupational Safety and Health, or NIOSH, is under the US CDC, and they publish data that can be used as a benchmark for permissible CO2 exposure. The permissible exposure limit, PEL, is based on 8 hours exposure. 0.5 volume percent is equivalent to 5,000 parts per million. Now, to give you some perspective, you can compare 5,000 parts per million to atmospheric CO2 level that has gone from less than 300 parts per million historically to roughly 400 parts per million today since the Industrial Revolution. The IDLH is immediately dangerous to life and health, which is based on a 30-minute exposure duration. The studies actually report intoxication at 5 volume percent after 30 minutes, but our recommendation is to include a margin for 4%. The immediate concern is that CO2 forms carbonic acid in the bloodstream and can potentially kill before asphyxiation occurs at 10% knockdown level. Mitigation involves multiple layers of protection. Good design practices to minimize leaks are, of course, important. Training and operator and guest guidance is an important layer, and any individuals present need to know how and where to react to monitoring systems. Fixed permanent monitoring is another layer that ties into procedures. And as a final layer, portable CO2 monitors can augment a permanent system and give an early warning to individuals at their exact location and time to react. Now, when we think about moving forward from the current pandemic, we must also consider how we can address climate change while at the same time sustain our economies and build a better world for all of us. The transition to minimizing greenhouse gas emissions will not happen overnight. For some industries, such as electricity generation, the transition will happen sooner, but there will remain certain industries where there is little alternative. Carbon capture, for some time, may remain the only clear solution for many of these. In the meantime, the public through government will continue to move toward a regulatory framework through taxes and CO2 pricing schemes, such as a carrot and a stick approach to change behavior. And finally, ESG, which stands for Environmental, Social, and Governance benchmarks for industry, are also more and more a consideration for obtaining investment for capital. And with that, I'm going to turn it over to my colleague, Matt, who will cover the next section.
Thanks, John. Carbon capture is a way to maintain and adapt a core business to meet new regulatory and environmental pressures. Some incentives for carbon capture are specific to industries. For example, Fluor is active in the LNG space, and in that area, carbon-neutral LNG cargoes have recently been sold to multiple companies, with the price premium quoted by Platts equivalent to hundreds of millions of dollars per LNG train. Other incentives, like direct government investment, focused tax credits, and cap-and-trade market systems apply across industries. Importantly, these incentives can be combined. For example, a liquid fuel producer in California can combine California cap-and-trade incentives, U.S. government tax credits, and low-carbon fuel credits. Other localities can combine the carbon value of enhanced oil recovery or the economic benefit of a shared pipeline system with these incentives. These combinations can bring the total incentive above the 35 to 45 US dollar per metric ton, which is required to break even for the carbon capture facility. And they can lead to a real rate of return to help finance a project. Many of these incentives are tied to government regulations that can, of course, be reduced with time. However, there's also a very real risk and opportunity that future political action can cause the incentives to further increase. Early actors may be in a position to both obtain near-term incentives now and also reap future cap-and-trade and other long-term incentives in the future. Carbon capture is not new. Fluor's key technology stretches back to the 1980s, and many facilities using many different technologies have been built to date. In North America, CO2 pipelines exist in the Gulf Coast, the Northern Rockies and Plains, and most recently in Alberta. These pipelines lead from both large and small-scale carbon capture facilities to geologic injection and oil recovery sites. The rest of the world, including Asia, the Middle East, and Europe, also has operating facilities in place. For example, the North Sea has seen CO2 injection for decades and is the current focus of both individual and collective efforts. One absolute key for any carbon capture facility is finding a good destination for the captured material. Some chemical syngas processes benefit from additional CO2, presenting an opportunity to turn CO2 into valuable product. And while not yet commercialized at large scales, new chemistries are under investigation to further the potential for reuse. The food and beverage industry also uses CO2 as a feedstock. Very large-scale processes generally look at geologic deposition of some sort, either in conjunction with oil recovery or as static storage. Methanol, ammonia, urea, and other syngas processes work off of a combination of CO2 and hydrogen. Some processes benefit from adding additional CO2 to adjust the ratio to produce more product. For example, Fluor has experience with the front-end design of a world-scale methanol facility to recover CO2 from the reformer furnace to increase the yield of methanol, directly turning waste CO2 into a saleable product. Expanding this concept, it is possible to combine recovered CO2 with green hydrogen to produce the same syngas stream that is needed by a methanol or urea facility, presenting an opportunity to produce these key chemical building blocks without a hydrocarbon feedstock. While not yet utilized at large scale, the product of carbon capture facilities developed today could be rerouted to facilities like these in the future if technology progresses. In Northern Europe, a robust greenhouse industry uses enhanced CO2 levels to increase plant growth in high-yield agriculture. Industrial carbon capture feeds these facilities through a pipeline system today. Large-scale facilities generally look to store CO2 underground. Large, porous sedimentary rock formations with an appropriate cap layer above can store CO2 deep underground. While specific geologic categorization has only been conducted for select areas, this basic geology exists worldwide, presenting good candidate geology for carbon storage on all continents. Importantly, the same rock formations that are good at storing CO2 are also good at storing oil. So formations with a history of oil exploration, likely located near existing industrialized areas, are proven possibilities for long-term carbon capture. In Europe, the North Sea is a key location. And to support this, a shared collective effort is underway to produce the pipeline and injection system for CO2 in known reservoirs. This allows the CO2 deposition portion of the equation to basically be a public or shared utility, making it easier for every producer in the area to consider carbon capture on their facility. The Alberta Carbon Trunk Line is a similar system that is operating today. The choice of destination depends largely on the amount of carbon involved. Small-scale systems fit well with greenhouses and beverage facilities. Large-scale systems may require geologic storage. I'll ask John to explore the options for taking advantage of these opportunities.
Thanks, Matt. Next, we're going to talk about what configuration options are available. Now, for convenience, we have divided carbon capture into three main categories: pre-combustion, post-combustion, and oxy-combustion. Some processes, like hydrogen plants, produce CO2 as part of the main chemical reaction. In these units, it's possible to consider capturing the carbon from a high-pressure, concentrated process stream itself. This is what we call pre-combustion. Most of the CO2 in the world comes from combustion that results in flue gas from a firebox. Since combustion usually operates at low pressure for safety and practical reasons, capturing carbon from the flue gas of a firebox has its own category, which is post-combustion. Finally, select combustion processes can use pure oxygen instead of air for burning directly, producing a higher purity CO2 product from combustion. While research and some demonstration scale facilities exist for this method, large-scale commercial facilities focus on the first two, pre- and post-combustion technology. And that is where we will begin our focus here today. A common pre-combustion capture application is from hydrogen generation, where CO2 is a byproduct of gasification or steam methane reforming processes. You may be familiar with the term blue hydrogen, which refers to hydrogen generation with carbon capture included. The pre-combustion capture piece is where a CO2 absorber is incorporated into the process stream upstream of hydrogen purification. Liquid solvents are most often used to absorb the CO2 and then are regenerated to collect a concentrated CO2 stream. It is quite feasible to retrofit hydrogen generation plants in this manner with fairly minimal interruption of the hydrogen production business. And in fact, our first example to present is a facility where we did just that. The Quest carbon capture project is located in a heavy oil upgrading facility near Edmonton, Alberta, Canada. This facility has 3 hydrogen plants generating a sum total of 330 million scuffs a day of hydrogen used for oil sands upgrading. The project uses an amine solvent technology with a central amine regeneration facility located closer to 2 of the hydrogen plants, while a 3rd hydrogen plant is located about 1 kilometer away and is connected by pipeline. The amine has a Shell-named brand called ADIPX and is essentially made up of an MDEA solution activated with piperazine so that it is selective for CO2 capture. This commercial scale facility was partially funded by the provincial and federal governments to demonstrate both the capture side and the safe sequestration of CO2 into the local sedimentary basin. Traditional utility grid interconnected power generation facility. Here, Fluor played an integral role in the project development of Quest, with Shell from the conceptual design stage through detailed engineering and construction to completion. The scale in this case is definitely world-class commercial, which you can tell by these pictures. If you look closely, you can see the size of construction workers standing on the ground next to these columns. The picture on the left shows a central facility with a large amine regenerator tower, and the picture on the right are 2 amine absorbers, each scrubbing about 100 million scuffs a day of net hydrogen producing gas. These absorbers are located adjacent to 2 out of the 3 independent hydrogen plant trains. Post-combustion. Post-combustion facilities connect directly to the flue gas of a firebox. For example, to the outlet of a boiler in this flow diagram. The flue gas is pressurized slightly in a booster fan, cooled if needed, and then the CO2 is separated out using an amine or another technology. The captured CO2 is compressed and the flue gas with nitrogen, water, and only a small residual amount of CO2 is sent to the stack. A key advantage of post-combustion is that it can be used with any process that has a fired heat source. Large refinery heaters, refinery FCC units, hydrogen plants, coal, and natural gas power are some of the places where it can be directly applied. A variety of carbon capture technologies are being explored at an R&D level worldwide. However, only amine-based systems are most proven and commercially practiced at this time. While amine-based systems are most proven, the flue gas conditions require a different amine technology than the pre-combustion system that I showed you previously. Generally, we at Fluor approach projects from a technology-neutral position where we implement third-party licensed technology, such as in the Shell example that I just showed you. However, Fluor has invested heavily in and does offer a post-combustion technology called ECONAMINE FG+. Fluor's ECONAMINE FG+ technology is an example of an amine technology specially adapted to the post-combustion capture. While any carbon capture system will operate best with a high CO2 concentration and low oxygen concentration, as oxygen does degrade amines, specialized amine systems like ECONAMINE FG+ are adapted to handle the conditions of flue gas. For example, we have used this technology with a stream as challenging as a gas turbine exhaust with a high amount of oxygen and a relatively dilute CO2 concentration. Amine-based systems have a large absorber to contact the flue gas with amine and a smaller stripper to then pull the captured CO2 out of the amine. Heat and cooling is required to operate the stripper. We have also demonstrated the ECONAMINE FG+ system on FCC flue gas, and as shown in this example, on coal to demonstrate the ability to handle different contaminants. Handling solid degradation is a key challenge for a post-combustion system, as oxygen will naturally degrade the amines. Multiple technologies are used to combat this. The picture pop-up on this slide shows the amine after a significant online time and demonstrates the effectiveness of these methods. Post-combustion capture can be bolted onto many different processes. A clustered collection of fired heaters or a single large flue gas source can be a natural feed stream to the system. Now, this is a proven technology with years of direct operating experience and a close relationship to the larger industry experience with amines. Okay, so now that we've highlighted some commercial applications in operations today, I'll turn the presentation back to Matt to cover some of the costs.
Thanks, John. One way to understand the cost of a pre- or post-combustion system is to look at an area where carbon can be captured both ways. A modern steam methane reformer hydrogen plant is an example. Without carbon capture, the plant operates as shown here. Natural gas goes through the reformer and shift reactor as part of the process, where it's converted into hydrogen and CO2. Hydrogen is produced as a product in the PSA on the right side of this diagram, while CO2 and other material is sent to the firebox. The firebox burns additional natural gas to provide heat to the process, and the combined flue gas contains both the CO2 from the heater and the CO2 that came from the process. Pre-combustion adds a carbon capture system in the reaction loop. This is the exact configuration of the Quest project that John discussed. The majority of the CO2 from the process can be captured, but that from the firebox is still emitted. Post-combustion instead adds a carbon capture system on the firebox. As all the CO2 from the facility is in one place, this provides an opportunity for a higher capture percent. The cost of a carbon capture system is based on the amount of carbon captured. In a minute, I'll discuss the economics of the two hydrogen plant configurations shown here, assuming that they are the same size. That is, they capture the same amount of carbon. The pre-combustion system at the top of the slide and the post-combustion system at the bottom are both the same size. Both capture 90% of the carbon that is fed to them, and both capture 2,500 metric tons per day of CO2. As shown on the numbers on the left, however, the pre-combustion system only feeds about half of its available CO2 into the system, as the flue gas never sees the carbon capture system. As a result, the host hydrogen plant needs to be twice as big to capture the same amount of carbon. Or put another way, the pre-combustion carbon capture plant only captures about half of the carbon that the total facility produces. Considering the hydrogen plant example, the biggest difference between the pre- and post-combustion systems is the absorber. The post-combustion system runs at a much lower pressure. As a result, the actual volume flow of gas through the absorber is 25 times larger in the pre-combustion system, as shown in the graph on the left. While flow rate is a key variable in sizing the absorber, it is not the only variable. The diagram in the middle considers the absorber size using the same packing at the same percent of capacity for both systems, one pre-combustion, one post-combustion. The liquid rate in the systems is similar. Both are capturing the same number of tons of CO2 using an amine of similar chemistry, so they need a relatively similar amount of liquid. And while the volumetric gas flow of post-combustion is higher, the density is lower. Liquid flow and vapor density are parameters that help determine packing capacity, along with volumetric flow rate. So while the volumetric flow rate differs by a factor of 25, the column diameter differs by only about a factor of 2. In terms of construction cost, the larger diameter of the column in post-combustion is balanced by its lower design pressure, multiple orders of magnitude lower. For this hydrogen plant example, post-combustion has 25 times the volumetric gas rate, but only about 2 times the absorber diameter, all else being equal. The design pressure is much smaller in the opposite direction. In terms of absorber cost, both pre- and post-combustion can be competitive with each other. Absorber size, construction techniques, and other factors will determine if one is more expensive than the other in terms of installed cost, which will vary between installations. The absorber system is one of the more expensive portions of the carbon capture equipment. But areas outside of the direct carbon capture system, the compressor, the pipeline, and the geologic injection system, are even larger. Any carbon capture system of any technology which is considering geologic storage needs to have a compressor, a pipeline, and an injection system. And these systems may consume a majority of the capital cost. For this hydrogen plant example, much of the carbon capture unit can be effectively the same between pre- and post-combustion. Starting at the bottom of the graph, the compressor will be effectively identical. With similar amine circulation rates, the stripper may also be nearly the same. We talked about absorber costs previously. These may vary due to construction techniques, site location, and other factors as much as they may between pre- and post-combustion systems. The main cost differences then are at the top of this diagram. Flue gas cooling may be needed for post-combustion. The solvent heating, movement, and conditioning equipment can vary due to many factors. Techniques like a semi-lean regeneration system and a lean vapor compressor can improve energy efficiency. Adding absorber intercooling can improve performance and also affect circulation and energy efficiency. An online solvent maintenance system can improve operability. While some of these systems are more needed in a post-combustion system, they all present optimization opportunities to trade off capital cost with operating cost. The graph at the left shows a pre-combustion facility where CapEx was a focus. The one on the right shows a post-combustion design where OpEx was a focus. The total cost difference for this hydrogen plant example is only about 35% between the two. Of course, there are many steps between these, where different trade-off decisions between CapEx and OpEx can be made in both cases. The gap between these two systems in this hydrogen plant example, when compared on a direct, equivalent size, apples-to-apples basis, may be relatively small. And it is important to note that the pre-combustion system still leaves half of the CO2 emitted to the atmosphere. A post-combustion system scaled up to capture the full output from a hydrogen plant may have a similar or lower cost per ton due to economies of scale. One key factor in the economics of any system is the integration with the larger facility. I'll turn the floor back to John to explore that in more detail.
Thank you, Matt. Now, if you followed along with us to this point, you may be wondering to yourself, how do carbon capture products best fit in actual application? And what sort of advice can we offer? First, let's talk about key project considerations at a high level. First advice is to look for synergies in your particular application. This may include your CO2 strategy, CO2 sources, and the sinks, things that we talked about like regional CO2 hubs and enhanced oil recovery. Every region has unique characteristics. The next is integration of utilities and the local infrastructure. Next is to select a proven technology, and here we emphasize proven. There are lots of R&D claims in this space, so do your due diligence. In proven technologies, process guarantees can be offered, but the key is matching expertise with each specific application. Next is practice execution efficiency. This, we encourage collaborative engineering, robust planning that is construction driven, and cost focused. Be schedule aligned, but not necessarily schedule driven, where bad decisions can add cost. And last is to apply relevant experience. And be engaging of the right people. So let's start with some examples. Now, any of the amine-based systems will require steam for heating, a means of cooling, and power for compression. One possibility is to pull these from the host facility. This diagram shows carbon capture in an electricity power plant, where steam and power are pulled from the host facility. While this is parasitic in this case, which effectively means derating the power plant, it is notable that some industrial facilities may operate with a relative excess of low-pressure steam that can be used for little or no economic penalty. While cooling water may not be similarly available, it can perhaps at least be combined with other users for economies of scale. A second option shown here is to eliminate the impact on the larger facility by using a purpose-built COGEN to balance steam and power for the carbon capture equipment. This adds another flue gas source, which can then itself be brought into the carbon capture system, but avoids any changes to the larger facility. Now let's look at the key drivers for the Quest project example we have used. On the surface, these key drivers shown here may not appear surprising, but for a one-of-a-kind revamp, they pose some unique challenges. Now, the initial thinking around energy optimization was to minimize utilities to likewise minimize the parasitic energy costs of capture. But what we found in this case is that the facility as a whole had sufficient utilities available given the fact that the refinery complex had an electrical power plant that was supported in integrated electrical power grid and was only utilized during peak power loads. So during the front-end development of this project, we collaborated closely with site stakeholders to unlock this opportunity. With the utilities opportunity identified, we were able to implement strategies into the design that focused on minimizing capital costs. One strategy example was an advanced modularization strategy to minimize facility footprint and also reduce the capital cost by minimizing facility interruption. An early process optimization exercise leveraged the available utilities to significantly limit equipment capital costs. Now, understanding this capital cost and operating cost balance allowed us to find the best fit. Now, how did this work? The key was in delivering an operating balance between carbon capture and electrical power grid needs. So to elaborate on this example, here is a schematic of the facility COGEN power plant. The COGEN only required its peak utilities during peak power demand, which it turned out is historically only required less than 5% of the time. For a majority of the time, the power plant was in a turn-down mode and available for the upgrader facility to island during grid power upsets. The situation is very common for smaller gas-fired power plants that have a lower overall efficiency than the much larger integrated baseload plants. Therefore, the CO2 capture plant used shared utilities with the COGEN steam supply, tied into the steam, the condensate return, and the cooling water systems. These systems were underutilized and available for CO2 capture when the power plant was in turn-down mode. So the power plant in turn-down mode and the carbon capture is in full capture mode with the hydrogen plant in operation. During peak power demand, carbon capture is designed to be turned off. The carbon capture on-stream factor is based on 90%. The grid peak power demand historically, as I said, is less than 5% of the time. It takes about 6 to 8 minutes to fully make this shift between the two systems. Once peak power demand is over, CO2 capture can continue. In practice, this did pose multiple engineering challenges, and some clever tie-in and control schemes were used to ensure that a seamless switching between the operating modes was allowed. Other key project drivers included maintaining the core business of producing the hydrogen and revamping with minimal footprint and interruption. This is a 3D model shot, which shows revamped scope within the hydrogen plants themselves. There are 2 hydrogen plant trains depicted here as a ghost image. In addition to the two amine absorbers shown on the right-hand side, near the stack, you can see where a flue gas recirculation system was used to modify the hydrogen furnace design. This flue gas system allowed a constant volumetric flow of gas through the furnace, and it allowed turning the carbon capture plant on and off. This demonstrates one of the several design features used to turn carbon capture on and off while minimizing the chance of upsetting the core business operations. The Quest project has been a proven success in pre-combustion capture. The plant started up in 2015 and is operating today at a nameplate capacity of over 1.1 million tons per year of CO2 captured and sequestered. And better yet, the project was delivered on time and below budget. So before we get into the Q&A, let's highlight a few things that we hope you take away with you today. The first is our belief that carbon capture needs to be a part of the climate change solution. Fossil fuel use may decline over time, but it is not completely going away for the foreseeable future. We highlighted the breadth of sequestration and carbon capture options. As the framework for regulations come together, we expect these options to grow. But most importantly, we hope that you take away a better understanding of the technologies and opportunities for integrating carbon capture into your facility. So whether or not the path forward is clear today in your particular world, it's best to start evaluating now to be prepared for the near future. Thank you for your attention, and let's go back to the moderator now for questions.
Thank you, John. Thank you, Matt. So we do have a handful of questions that have come in. First, you mentioned that CO2 capture costs at $35 per metric ton. What scale facility is this cost based on?
Sure. So the cost of facility certainly can depend on the size due to economy of scale factors. The numbers quoted are for a relatively large scale facility of the types that we have built for both ECONAMINE and other technologies the world have seen. And that cost is for essentially a break-even cost. What is valuable is that in many parts of the world, incentives can be combined to give a higher value than that can provide a rate of return to help finance the project as well as simply paying the owner's costs.
Thank you, Matt. And just as a reminder to our audience, if you have any questions, please type them in the Q&A panel and address them to all panelists. So on slide 39 and 40, you described the installed costs. And what are the operating costs?
The key operating costs are energy in terms of regenerating the solvent, which is usually in the form of steam, power, largely in the form of the compressor. Those are the two key operating costs. And the way those costs impact the facility depend directly upon how the facility is integrated. John mentioned some examples of how that integration can be done to minimize the total costs. And a facility like a refinery that may have additional low-pressure steam available can utilize that to help offset some of those operating costs.
Yeah, and we look at operating costs of facilities. You know, a lot of it does depend on the integration and whether that operating cost is new capital requirements or is it a toll type of requirements, like it's tied into a power plant or another facility. So there's quite a bit of variability, but the operating costs can be in the order of 20 to 30% of the cost. And it's really a balance between figuring out the contribution of the operating and the capital, which was one of the optimizations that we tend to do early on in a project and is an important key consideration.
Thank you, Bo. Do you have experience with direct air capture of CO2?
That's a good question. We've talked to some of the companies doing the direct air capture and are familiar with their operations. One of them, my location, having done a lot of work in Canada, Carbon Engineering is based on the West Coast here. We have not, we've been in discussions with them. I guess we're not specifically developers per se, in that we've been focusing most of our efforts on industrial commercial applications. I find direct air capture very interesting. I guess our philosophy has been to go to the source of the major emitters, and therefore we focused on more the commercial industrial scale as opposed to direct air capture. But we certainly, from my standpoint, certainly follow it very closely.
Thank you, John. Next question. Are there any poisons to the carbon capture amine circulating absorption fluids?
So the post-combustion system with the oxygen present certainly does provide many opportunities for amine degradation. Also, post-combustion systems, particularly in a coal-fired or FCC flue gas type scenario, introduces the possibility of other contaminants. Much of the work that we've done on the ECONAMINE process has been to try to overcome these issues. And as John showcased in one of the slides that he was presenting, we have put a lot of effort in developing methods to make sure that the amine quality and amine hygiene can remain quite high, due to even in the face of long-term operation with high oxygen and contaminants in the stream.
Yeah, I have one thing to add to that. On the post-combustion, the final flue gas is emitted to the atmosphere after the CO2 scrubbing. And the history of the technology has shown that, especially in the 90s with some of the work done in the North Sea, that there were side reactions of the amines with the oxygen to form some nitrous type oxides that were being emitted, and mitigation has been put in place to deal with that and to ensure that the final emissions, which are emitted to atmosphere, do not include any potential contaminants or side reactions which may occur. So that has gone through some of the early generations, and is in fact an example of how the technology has evolved to understand what are the potential hazards and to mitigate and put in design provisions to help mitigate and avoid any future hazards that may occur. So the designs have adapted over time.
Thank you. Our next question, are there any amine emission concerns or permitting issues with CO2 capture facilities?
Absolutely, there can be issues with that. That is one area where ECONAMINE FG Plus has a real advantage, that the amine used has an inherently lower emission rate, and we have worked hard to make sure that technology keeps that low.
I was highlighting some of those emissions concerns that were found in the early generations of the technology, and those are true. The other thing I'll add to that would be that, you know, the process guarantees can cover emissions. So the technology supplier, and whether it's Fluor or anybody, really should be taken to task that the guarantees also relate to what is actually, you know, what are the potential hazards that could be emitted to the atmosphere, so that they're held accountable for any potential emissions that could result.
Thank you. So how does Fluor ECONAMINE FG Plus process compare to other post-combustion CO2 capture processes from our competitors in terms of removal efficiency?
In terms of removal efficiency, it is extremely competitive. Fluor's ECONAMINE FG Plus process can achieve 95% removal of CO2 from the effluent stream. In general, CO2 capture processes can achieve a relatively high percentage of CO2 captured. Whether or not all the other processes can get as high as 95 is one that you'd have to look at for your exact application.
what we've seen in this space is that very specific to the applications, some of the amines can be challenged, whether that's degradation in oxygen, which we talked about, or other types of contaminants. And the thing is once that design basis is established, there's quite a bit of decisions and capital that get invested and involved in building the system and putting it into a place, getting it started up, and getting it operated. So the technology supplier should be the most experienced, or at least the most having the most profound understanding of what those potential contaminants, problems, and issues may be, because once the capital is in place, it takes a large amount of time and effort to change something. As after the project starts up, and let's say it's found that the amine or whatever solvent degrades more than expected. And that can lead to quite a number of headaches, additional capital investment that's unforeseen, and higher operating costs if solvent replacement is the only short-term solution. So these types of problems we've seen in industry, and we've focused on the ECONAMINE FG Plus process to overcome these problems and anticipate them and put in some years' experience. But they do occur and we've experienced them in other solvents with other third-party technologies. Many, whether or not we can anticipate them or not, it is best to regardless of technology, to build a good example of why to build that network of expertise in order to understand and then address those potential issues to minimize interruption and achieve the expectations from the project.
Thank you. Next, how stable is the solvent? What are the materials of construction of the CO2 absorber and regenerator? Sorry.
Well, I'll jump in there since I have, I was the lead engineer on the Quest project, and I guess starting with the materials, carbon dioxide and water form carbonic acid, and as we know from drinking soda pop, many of us since we were kids, we know that it can be very corrosive. When you drop a penny in a glass of Coke, it's a great way to clean a penny. And so that directly affects the materials of construction. And so there's a lot of stainless steel. Anything that carbonic acid can touch requires a high corrosion resistance. And most of the equipment, from the flue gas system or through the, as soon as the amine or any other water-based solvent contacts CO2, the pH or the acidity of that stream will be quite low or quite acidic, and most of the system is stainless steel. It's stainless steel up and through the compression, where the dehydration of the CO2 occurs as it's being compressed into a high pressure supercritical state. So there are a few solvents that are not water-based and can avoid that. So that is a consideration for water-based solvents that contact CO2 and handling that acidity.
Thank you, John. All right, so next we have a cluster of questions around financials. So the first one, can you provide a ballpark CapEx cost as % of main process facility CapEx costs? So for example, a process facility that had a total installed cost of $1 billion, what would be the CO2 capture facility CapEx cost?
Yeah, it's difficult to name the cost on that basis. The best way to look at the cost would be on the idea of a cost per ton of CO2. For the CO2 capture facility, what it really cares about is how much CO2 is it capturing. That's the number that matters. Whether it's from a heater, which is a very small part of a really big refinery, or whether that is from a piece of fired equipment, which is the entirety of the process, obviously will determine what the CO2 capture cost is as a percentage of that total facility, and will vary by quite a large ratio between those two examples. But on the basis of capture costs in terms of per ton of CO2 captured, that is a much more stable number, because there the key influencers are the economies of scale of the facility, the decisions between CapEx and OpEx, between pre-combustion and post-combustion that I was discussing in the economic analysis. Those are factors that really do influence it, but they don't influence it by a order of magnitude type number. They influence it by a tens of percents type of value, depending upon where you move within some of those ranges. So in terms of for if you want a more detailed answer for your exact situation, that's something that, of course, Fluor would be happy to talk to you in more detail on. And I'm sure at the end of this, there will be some contact information. And please do get in touch with us, because we would like to help answer that question for your exact facility in a way that will be more beneficial to you in your exact operation.
Thanks, Matt. So another along those lines, what's the ROI on the differential for the capital invested between pre and post-combustion systems, roughly, of course?
Yeah, so if the relative capital cost is not significantly different, but you're in an example like the hydrogen plant example, where the post-combustion system can capture twice the CO2, then you'll obviously gain twice the economic incentive there. And if you are in a political and geographic location where you can utilize multiple incentives to give a real rate of return, then that can, of course, really pay out. The economic numbers that I was giving were focused on that hydrogen plant example to give something real to hang some costs to. Obviously, pre and post combustion can exist in other types of process systems, and for those, the relative ratio of how much carbon you can capture in each system, and thus the economic incentive, could be a bit different based upon the process economics.
I'll add one thing. I don't mind deferring the cost and economic questions to Matt, because they're a lot harder to answer. But one thing that we're seeing lately is the clean fuel standards that are coming out. They're coming out in California, in jurisdictions in Canada and Europe primarily, and I imagine they'll follow in other states or other jurisdictions. But the reason I mention that is clean fuel standard really looks at the carbon intensity of fuels that we're putting into our gasoline or diesel-powered automobiles. And there are certain credits associated with that grow and change over time, but they've changed the economic picture for a lot of transportation fuels. And that has become a unique driver in trying to determine what the rate of return is. But those incentives do compound, and they're significant. I mean, if in the published data, returns on CO2 capture on the order of, we mentioned 45. We've seen numbers up to $60 a ton. But in that range, if you add on these clean fuel standard incentives, the numbers calculate out over $100 to $200 per ton of CO2. So it's just demonstrating significant incentives, but those incentives are gained through the sale of low carbon intensity fuels. And whether you're producing those originally from oil and gas processing, or whether they're biofuels or other types of fuels, it's that carbon intensity of that has created some unique incentives in certain space.
just to add to what you mentioned there is a report in the public literature noting that a upstream oil producer can achieve quite a good economic incentive of hundreds of dollars a metric ton, and for a potential carbon capture where the for example, for a power producer or which is tied into that upstream oil production facility, the same can apply to a refiner. And there is a real opportunity for refiners in places where the same low carbon fuel standard type of legislation, which is driving renewable diesel and other biofuels, that same legislation can potentially be harnessed for carbon capture. And the cost of the carbon capture may be a lot less than the differential cost between soybean or canola oil and crude oil. So there is a real opportunity for carbon capture in refining systems due to legislation that perhaps was originally aimed to drive biofuels, but those same incentives can be captured in some cases for carbon capture as well.
Well, I think we're near conclusion here, and I'm sure there's a few other questions. But I can sort of end this by saying that I want to thank the audience for the opportunity. It's been a joy to share for the last hour this subject with you. And, we've been quite involved, Matt and I, and we also did an earlier presentation in the Europe time zone with Michel Barnes, who is our colleague there. That we collaborated with on this presentation. So it's something that we are passionate about, and we will continue to look to developing these projects worldwide in our jurisdictions, and hopefully continue to expand it to other industries and businesses, and just to aim at making building a better world. So thank you very much.
John, it appears we're having some technical difficulties. Let's just wrap up the webinar here real quickly. We'd like to welcome you to the next webinar, which is scheduled for Thursday, October 8th, 9:30 a.m. Central Time. You can stay connected to these events or future events, and we encourage you to visit the Innovation Builders page on Fluor.com or follow our social media channels using the hashtag InnovationBuilders. If you have any questions, you can send them to innovation.builders@fluor.com. Thank you for attending.